Hello everyone and welcome to this next lecture. We are going to discuss the very basic image enhancement techniques, how to improve the quality of an image. So far we have seen how to geometrically correct the image, and but now in this one we will have discussion on basic image enhancement techniques, very simple one. But before that, just I would like to recap or refresh your memory, saying that remote sensing images are nothing but a two-dimensional matrix. It is a raster data, and each cell is having a pixel value, and that pixel value is in terms of positive integer values. And over this shape of a cell, in this case we call as a pixel, would be a square shape. However, overall shape of an image or this two-dimensional matrix can be either square or rectangular. That means number of rows and number of columns need not to be same. They can be different, but the cell shape has to be, that means the pixel shape has to be square in shape, and each pixel is having a value, and that value is in integers. And if I am having more number of bands, like here bands k, then I may be having pixel values depending on the which part of wavelength these bands are representing. They will carrying the different values. In this particular schematic, like for green band, they are showing some other, for blue, red and black. So four bands are together are shown here, just it is a schematic. And a digital number for say column 5 row 4, column 5 row 4 is expressed as VB542, and that if I want to add it or make it something, then it is going to be so I can address very easily as well by using column number or row number. Now when we get the data from the satellites, that is the data acquisition, we will see very quickly about data acquisition part as well. We store the data in certain format. For image, there are few formats which are followed world over, and nowadays the images which are available on net free of cost, like Landsat images or other images, generally they are already georeferenced, and if they are not georeferenced, no problem, we can do the georeferencing as well. But before that, the raw formats which are used are three main, most popular one are the three. The first one in this is the BSQ format, that is in short BSQ, but we say band sequential format. So that each line of the data followed immediately by the next line in the same spectral band. So it is a band by band formatting. So suppose it is a Landsat MSS data. Now there are 4 bands. So the first band would be written in a file, then the second band, then the third band, then the fourth band. Now there are advantages with writing or making such formats, following such formats, that if I am interested to read only band 2, then I will jump in while reading through my program to band 2 and read the entire data. But if I am interested to read all 4 bands of a particular area, not the entire image area, then this type of format is not suitable. So people designed another format which is called band interleaved by pixel format. That means the first pixel of all bands in sequential order. So first pixel of first band, first pixel of second band, first pixel of third band, first pixel of fourth band, and likewise if there are 4 band, then will come second pixel of first band, second pixel of second band, and likewise, followed by second pixel of all bands, followed by the third pixel of all bands, and these are interleaved up to the number of pixels. So if an image is having say 512 columns, it will go till 512. This format provides optimal performance for spectral access of image data, good for hyperspectral images, because hyperspectral remote sensing is parallelly very nicely developing, and therefore for such kind of images this BIP or band interleaved by pixel format is going to be very good. And the third type which is very popular is BIL. BIL format, band interleaved by line. Here instead of pixel, entire line, that means one row is written first for band 1, then first row of band 2 is written second, and likewise. So, the first line of the first band followed by the first line of the second band followed by the first line of the third band, interleaved up to the number of bands. So, if there are 4 bands, then all first lines of all 4 bands are written first in sequence, then second line of all 4 bands are written, and likewise. So, subsequent lines for each band are interleaved in similar fashion. This format provides a compromise in performance between spatial and spectral processing and is recommended file format for most NV processing tasks, good for images with 2060 bands. So, this is another issue, because now we are also going for large number of bands, means our spectral resolution is also improving, and for that BIL format, this NV is a soft image processing software, but many softwares are having their own format. NV is having a format which is BIL format, like ERDAS is having its own .img format, or another very popular image format is a GeoTIFF, which was a TIFF format. Now, the another version of this TIFF format, which is called GeoTIFF, it is also having geographic coordinate written first in the image. So, that format is very popular. Many satellite images, especially like Landsat and others, are already georeferenced and available in GeoTIFF format, and they are ready to go for any image processing softwares or on GIS platform without any requirements of georeferencing. So, first the raw data once comes, it is written either in BSQ, BIP or BIL form as per the requirements, as per the number of bands, as per the size, as per the for what purpose they are being recorded. And of course, it is possible to change from one format to another, means from BSQ to BIL or BIL to BBP, BIP can be changed, but it requires further reading and checking of accuracy. So, likewise here in this for different bands, this is how we write. If we want to write for one combination, then probably this is one approach, and in case of BSQ, this is how the first band, first line, first the band 1 is written, then band 2 is written, band 3 is written, band 4 is written in case of BA, and in case of this pixel or BIP, then this is how, and then or first pixel of first band, first pixel of second band, and likewise you can check also the values, and then the BIL, the line by line. So, here the first line, then second line, then second line is the first line of band 2, then this third line is the first line of band 3, the fourth line here is the first line of band 4, likewise it is written. Same thing here, that the image one band at time, in other words the data of all pixels of band 1 are stored in this. This is very convenient and very easy to understand that bands are written in sequence. The first band is written first, second band is written second, and so on so forth. But as I have mentioned, that if I am not interested in the entire image area, I am interested only in the part area, and my image size is very huge, then this format is not very efficient one. Then probably BIP or BIL are going to be much more. So, band interleaved by pixel, that is BIP format, is similar to BIL except that each pixel is written band by band. And then here this third one is the band interleaved by line. The data is stored pixel information band by one for each line, row. An example, given a 3 band image, all 3 bands of the data are written in row 1, and then so on so forth. So, likewise we can write the data as per our requirement. We can change from one data format to another as well. As I have mentioned, first the image is acquired, that is the data acquisition. It is done through satellite earth stations. I will just show you. We have already seen one NOAA AVHR Earth station which is operational in IIT Roorkee, that I will show you. So, the first thing is the image acquisition. So, once the satellite has scanned a part of the earth, the image has to be acquired by the earth station, and once the data has been acquired, then other steps will start, that is the image processing. And basically making geometrically corrected image, one step, another one is improving the image quality so that our interpretation, visual or machine based, becomes highly reliable. So, for that we go for, and the third one is image classification. After enhancement, one may go for image classification, creating some output maps like land use map, forest density cover map, a lithological map, a soil cover map, and so on and so forth. And finally, one would like to assess the accuracy part after doing image classification. So, these are the broad 4 steps: data acquisition, image acquisition, as I have said that it can be done by satellite earth station. These figures or slides are repeating here just for the completeness. I have kept here. You need to have a antenna, rotating antenna, tracking antenna as shown here. Then you have to have a receiver, and then a computer system which will acquire the data and keep the data as per your desired data format. Once the data is in the system, then the processing starts. So, basically if we define what is basically image processing, is that image processing includes, it should be read as image processing includes enhancing an image, extracting information features from an image, and the computerized routine for information extraction, that is a classification, pattern recognition from satellite images to obtain categories of information about specific features. So, image processing includes image quality and statistical evaluation. So, we also try to assess what is the quality of an image. We also try to perform some statistical processes on it, and because before we go for further processing or enhancement of the images, we must know what is the minimum value in my image, what is the maximum pixel value, what is a standard deviation, how pixels are distributed. That prior information will help me to decide which enhancement technique would be better for my that particular image. So, this statistics is image dependent. Each scene, even of the same area belonging to 2 different seasons, will have different statistics, because images are going to be different. So, that is why before we choose for appropriate image processing technique, image enhancement technique, we must first assess through or do the evaluation through statistical analysis. Then of course, radiometric correction, as I have been saying, this is generally done by the operators of the satellites. Geometric corrections has to be done by the user itself, and for especially for higher spatial resolution data, this has to be done very accurately, very sincerely. Image enhancement and sharpening as per the requirements for what purpose the satellite image is going to be used. For keeping that thing in mind, accordingly the enhancement, the image quality enhancement and sharpening, that is done through the spatial filtering, which we will discuss in next lecture, can be done. And then finally you reach to the stage where then you can go for feature extraction, that is image classification, maybe pixel based, maybe object oriented based. Nowadays many very innovative image classification techniques have been developed, but the problem with these techniques is that they might be good for one particular image, but if I get the same area image of another season, apply the same way the image classification technique, I may not get the same results. So, because not only the season has changed, but the entire statistics has changed, entire image has changed, and therefore the results may not be that good or accurate for image classification. It becomes sometimes a scene dependent image classification, but anyway that will be discussed later. And once you go for image classification, of course we go for accuracy assessment, and that how accurately the image classification, a land use, suppose if I have classified an area as a bare rocks or bare soils, then really on the ground it is there, and how accurately I have classified. For that, a quality assessment about the accuracy has to be done. And then I take that classified output image to in a GIS platform, use it, or may create some more products using it, that is possible. And if I am going for time series data analysis, then I may go for change detection studies. For example, if I am using thermal images, I have created a output that is a sort of image classified output like land surface temperature map, that LST map. And if I am having a time series maps, LST map of the same area of different dates, then I may see the changes which has occurred between say 1 month, 15 days or 1 week. So that change detection can also be performed. It is need not to be that change detection has to be only after classification, even before classification can be done. So it does not matter, but change detection is only possible once we are having a time series data. At least 2 images are required. Suppose there has been an earthquake, and I am looking the ground changes, especially on the slopes of the mountain, whether some landslides have induced earthquake induced landslide have occurred or not. So I need an image which is just before the earthquake, and preferably the same satellite image, same sensor image after the earthquake. And if the dates of these 2 images are very close and in between the earthquake has occurred, then change detection with high reliability, high level of confidence can be done. And then I can conclude that whatever the changes which I am seeing between pre-earthquake image and post-earthquake image are induced by that particular event which has. So that event might be earthquake, that event might be a landslide, that event might be flooding, drought or any other thing. So it depends on the phenomena and then the availability of images for change detection. Change detection is becoming very powerful, very useful thing nowadays because of we are having long availability of archive of data. Now image quality, which ultimately if image is good, then interpretation will be good, classification will be good, everything would be having better results. So many image remote sensing data sets contain high quality accurate data. Sometimes error or noise is introduced in the remote sensing data, that might be because of environment and atmospheric scattering, cloud, maybe haze, fog, mist. All these environmental factors may deteriorate the image quality. For example, like if time is not, season is not that important, then the image which has taken just after the rain, especially say for in case of India, especially in northern India, where in winter time you are having generally very hazy scenes. So if an image is taken just after the rain when sun is there, you would find a very high quality image because the environmental or atmospheric distortions would be minimum. No haze, no fog, no clouds, nothing except the sun illuminating the surfaces, and therefore high quality image can be acquired. But then you need to have a orbiting satellite there at that time. Random or systematic malfunctioning of remote sensing systems we have discussed in previous topic while discussing the georeferencing can be corrected to some extent by involving georeferencing, and if there are some random things, then probably by human interventions can be corrected, and sometimes some errors are so bad that they cannot be corrected and such images cannot really be used at all. So, but one thing one has to remember that the generally image processing we divide in 2 steps. One we call as pre-processing, another one is processing, not really post-processing but processing. So this pre-processing basically involves the georeferencing and conversions. Earlier when we always never had the digital satellite images, we used to scan or convert by some means analog to digital, and that was considered under the pre-processing. Georeferencing can also be considered under pre-processing subheading. So, this improper pre-processing may bring some problems later on in your data analysis. Now, as I have mentioned that in this image processing, image enhancement, that is improving the quality of image so that our interpretation becomes easier and accurate. For that, we need to first understand the statistics of all individual images. As I have also mentioned, that an image of the same area taken in 2 different seasons will have 2 different statistics. So, each seed, the statistics of an image depends on that particular scene or image. So, if I see here the histograms, which is nothing but the here I am having the pixel values, suppose it is 8 bits of 0 to 255, and I am having frequency, and that is a typical histogram. If it is all well distributed, that means the value 127 is going to be in the center and the highest, then all our mean, median and mode all will be the same, and this in this condition we call a normal distribution. Though in real images theoretically it is possible, but in real images one never gets such kind of a normal distribution in the histogram. You may get a skewed kind of distribution of pixel values and their frequency. So, mean might be here, median is elsewhere, and mode is, that is the maximum, is the threshold might be different. And there might be a positively skewed, there might be a negatively skewed, and this is negatively skewed the one, this is positively skewed one, and there might be multinodal distribution. So, there are a kind of 2 sets, and this is possible because half of the image might be having a forest area, half of the image might be having agricultural land, and now both are having vegetation, but their signatures in an infrared channel are going to be different, and therefore I might be having bimodal distribution. So, it depends. If it is a desert kind of area, I may get a distribution something like uniform distribution, or it is a water body or a completely dense forest, I may get a completely distribution. So, based on this, this is the first step as mentioned here in the image processing to check the image statistics. The mean is the arithmetic average and is defined as the sum of all brightness value observation divided by the number of observations. The median is the value midway in the frequency distribution. One half of the area below the distribution curve is right of the median and the other half on the left, and the mode is the value that occurs most frequently in the distribution as shown in these examples in a distribution and usually highest point on the curve histogram. It is common, however, to encounter more than one mode in a remote sensing data set, as mentioned here is a bimodal, and this is very common thing, it is not very rare depending on the objects which are present within one image. Now, in image pre-processing steps, basically to create a accurate representation through geometric corrections, that is already discussed under georeferencing. Then radiometric corrections generally we do not perform, it is done by the operators itself, but if they have not done, we have to find some utility software programs to do it, but need to have lot of data about the sensor. Atmospheric corrections are also performed. Again, there are certain models which are used to remove atmospheric distortions from the images, but those models will also require lot of input about the ground conditions when the image was acquired, and that becomes very difficult to find. So, what we go for improving the image quality is to go for image enhancement. That may minimize the atmospheric distortions and other problem. Of course, geometric distortions has to be corrected using georeferencing technique. An image can be ordered at different levels of correction enhancement. The agencies, like in India there is a NRSA, NDC, National Remote Sensing Agency, NDC is National Data Center, they provide data about Indian satellites. You can order a completely processed data or you can order a raw data. So, if you are having capability of processing by yourself, you can buy raw data at a cheaper rate, of a large area and process yourself. So you will have your own confidence rather than depending on others. But if you do not have the capabilities and so much setup, you can directly order the complete correction, corrected and enhanced image data. Rectification, as we have discussed, to remove distortions. Here rectification has also involved the atmosphere, but generally it will be putting in the atmospheric correction technique. Initially when we had this MSS, or later on also recently it was noticed in case of in Landsat 7, and this stripping or de-stripping and noise removal. So that also we put in this because these are errors due to the sensors, and so this radiometric correction is a pre-processing method to reconstruct physically calibrated values, correcting the spectral errors and distortions caused by the sensors. But you need to have the information about, suppose I am having this data has been acquired by linear array. So whether these if these all CCTs have been calibrated perfectly, then the stripping, de-stripping noise will not come. But if they have not been, then this stripping or lines in your image will appear, and in order to correct that one, we need to have the data about individual CCTs, and if once we apply that correction, then spectral errors, that is creating stripping, de-stripping can be removed. For example, here that this is because of stripping. So de-stripping can be done once the data is available about individual CCD, and a smooth image can be generated. Drop lines, sometimes there might be drop lines, especially in the thermal data set it has been observed, because of saturation, because of high temperature value objects present on the earth. So it takes some time to cool down the sensor, and therefore there might be some drop lines are commonly replaced. Manually it can be also done. If there are not many drop lines, then manually perhaps these can also be replaced. In radar data you will find lot of speckle or noise, that too can be removed and your image can be made very smooth, and so the interpretation of such images can, but it will only happen in case of normal passive remote sensing when your sensors have not been nicely calibrated. Now atmospheric corrections, which requires a lot of input, these distortions might come from various reasons. So solar radiation is largely unaffected as it travels through the vacuum of space. However, when it interacts with the Earth's atmosphere, it is selectively scattered and absorbed, and the sum of these two forms of energy loss is called atmospheric attenuation, and this introduces the distortions in your image. The general goal of atmospheric correction is to turn digital image brightness value recorded by remote sensing system into scaled surface reflectance values. That means removing the entire effect of atmosphere from an image, assuming that there were no atmosphere. In some earlier lectures I have mentioned that on the earth we are having a thick atmosphere, relatively thick atmosphere, but on the moon we do not have we are having very thin atmosphere, and therefore atmospheric distortions are also very less, and therefore the images which are coming from the satellite which are orbiting Mars surface like Mangalyaan are giving a very high quality images, because there are no distortions due to atmosphere. But if we are looking the similar kind of image quality, then these have to be removed. Now the atmospheric conditions globally are not the same. In one area they are different, another area they are different, and one time they are different, in the same area in afternoon they are different, in evening they are different. So when the data is being acquired, all the inputs which will go for atmospheric corrections, the ground data has to be collected from that image area, then only we can go for high quality atmospheric corrections. If we use some models, then lot of assumptions are involved. So these values can then be compared to use to conjunction with the scaled surface reflectance values obtained anywhere else on the planet. So if we go for that kind of thing, then that means we are going for modeling, assuming that things are same at two different places or in within one image, and that kind of assumption for a coarser resolution data which covers a very large area may not be very good. There are, as I have mentioned, that if we go in much detail in this part, that atmospheric correction required, because there are a lot of phenomena, scattering, absorption, refraction, reflection, all are happening at the same time. This is the illumination source, this is the satellite, and while the signals going back, all these scattering, absorption, refraction and reflection are occurring, and it is a long distance. It has to first pass from atmosphere and remaining in the space. So, there are several ways to atmospherically correct remote sensing data. One some of relatively straightforward, while others are complex, being founded on physical principles and requiring a significant amount of ground data to function properly. This example is shown as that an image which was suffering from some atmospheric distortions like haze and other things, once those things have been removed, then an image quality has definitely improved. So, after image corrections using this model, one can really sometimes can improve the image quality. One another way of removing or improving image quality is applying a brute force correction that is possible by using a simple histogram stretch. So, if assuming that in an image value should have been 0, as well as some pixels should have carried value 0, another should have carried 255 if I am discussing an image of 8-bit, then I can stretch, and this is called a brute force stretch kind of thing, and if through this process in a very straightforward manner I am also removing the distortions which are causing probably by the atmosphere. But this is not a very standard method for removing atmospheric distortions, but if there is no other choice available, then probably this linear stretch of a satellite image can be applied, and then these distortions due to atmosphere can be removed. Now, image enhancement, further we are discussing that improves interpretability of image by increasing apparent contrast among various features. Basically, we are looking more contrast so that individual objects features can be identified very easily. That is the main purpose of image enhancement. Now, contrast manipulation, that is contrast stretching, maybe spatial feature manipulation, that means spatial filtering, which we will discuss in next topic. Spatial filtering, edge enhancement, maybe Fourier transformations based on this Fourier analysis based on fast Fourier transformations, multi-image manipulations instead of doing only on one image, and generally we are having choices of several bands, so we go for multi-image analysis, maybe some techniques like band ratioing, principal component analysis, vegetation indices, like a normalized difference vegetation index and so on and so forth. And so, on one variable, that is one single band, on multivariable multivariate analysis can also be performed. So, whatever the techniques which are available in mathematical domain for matrix or matrices can be used also in image, because after all it is a two-dimensional matrix. The example here of removing this thing is like this, that this is the original histogram, this is how this image histogram looks bimodal, and the values, the minimum value in this input image is 84 and maximum is 153, whereas it is expected that these values should have been 0 and 255. Need not to be, because it is not all the time that you will have a object in a single image which will have almost no reflection, and same time you would have an image in your a pixel in your image which will have the perfect reflection in 8-bit image, that is you will achieve 255 value. So, if it is not, then a simple linear stretch redistributing the values between 84 to 153 into 0 to 255 can improve the image quality, and this is also called the brute force, and indirectly you are also getting rid of some effects of atmosphere. And definitely this is the most common one, very simple one, straightforward one. You are treating each pixel in the same way. A linear stretch will improve image quality very quickly, and this kind of image enhancement is called linear stretching. Now same example here is that histogram is distribution is this, minimum value is 60, 158 is the maximum value. If I redistribute without any stretch, then it is going to be like this, but if I do the linear stretching, then I am using whatever the range of pixels available to me, that is between 0 to 255, instead of original range which is available between 60 to 158. So when I stretch these linearly like a rubber seat, then I am improving the contrast in the image and ultimately image quality by a very quick method. So here the input pixel values are 60 to 158, after stretching they will become, and so that once the values have been redistributed, definitely the contrast among different pixels, that means different features, will improve and will be higher. There is another way of doing is the histogram stretch, that now instead of just changing the value along the x-axis, now I am involving the frequency of pixel values, occurrence, and then histogram stretch, that wherever the frequency is higher, that area, those pixels will be stretched more, and wherever the frequency of pixels is less, those areas will be stretched less. And why this we call as histogram equalization, and the values which were between 60 to 92 have been stretched between 0 to 255, and wherever I had the more density of values are stretched more or more frequency of values. So this is called histogram equalization, and there the changes which you can see very easily, that how when this histogram was stretched, then the frequency will change and my image may look altogether different. And this is another example of histogram equalization, that I am changing now, playing with the frequency of occurrence of pixels and creating a different kind of contrast in image. So here you can see in a zoomed part also you can see the distribution. So definitely image quality has improved. The pixels which has the high frequencies are kept as it is, but pixels which has the low frequencies are giving more stretching. So it's in that way one way of doing this. So this brings to the end of very simple basic techniques of image enhancement by which you can improve the image quality. Thank you very much.